Thank you very much for this very warm and nice introduction. I would like to begin my talk with thanking the organizers of this very nice event. It's my, fifth or sixth time here in Armenia, and every time is very much enjoyable, and I'm very much looking forward to already returning next year. So it is a great honor for me to close this workshop on operator theory and harmonic analysis. Yesterday I have restructured it a bit, and today I plan to give a brief overview on the optimization methods in both continuous and discrete time, and then highlight our contribution to this topic, and then make a connection to the operator theory, which is the topic of this workshop, by saying a few words about the conjecture, an open problem in convex analysis, which is not solved for more than 30 years already. So, without further ado, let us begin with the very basic optimization problem of minimizing a convex, for simplicity, continuously differentiable function phi over the entire Hilbert space. So we are in a Hilbert space framework, as usual, nothing specific here, and we're looking to minimize a convex continuously differentiable function. Okay, so there are several ways, of course, how to approach this problem, through algorithms, through continuous time methods, but in any case, what we're aiming for is showing the fast convergence rates of the function values to its minimum. And for instance, let's consider the model example. How do we do this in a continuous time optimization? We take a second order in time differential equation. We link the gradient of the objective function phi. So if you remember, phi was the function to minimize. We link its gradient to the second order in time differential equations. And we show that alongside the trajectories xt, which is the solution of this equation, the function converges to its minimum at a certain speed. So for the rest of the talk, f star will denote the minimum of the objective function. Okay, so this is one point. The second point which we are looking to prove or to show is the weak convergence of the trajectories to a minimizer from a set of all minimizers of the objective function. So the trajectory xt is the solution of this equation, and we would very much like to show the weak convergence of those mentioned trajectories to a minimizer, to one of them, of the objective function. Now, in the title of my talk, Tikhonov regularization is mentioned. So what's the point? The point is as follows. We introduce an additional term to our equation here, as we will see later, in order to, well, first of all, preserve the fast convergence rates of the function values, so preserve the very nice speed of convergence of the function to its minimum, and improve the weak convergence of the trajectories to a strong one. So this the presence of the additional term influences, its influence lies in improving the weak convergence of trajectories to the strong one. Okay, not only, but to the strong convergence of the trajectories to the minimum norm solution, which is the projection of zero onto the set of the minimizers of all of the objective function. So suppose that this is the set argmin f, right? Or argmin phi in our notation. We're in a Hilbert space. We take the zero of the Hilbert space, we project it onto this set, and yes, that's basically our x star. So the definition is the projection of zero onto the set argmin f. Now this projection is unique because the set of the minimizers of the convex function is a convex set. Yes, so how do we introduce this additional term? Well, as the name says, we regularize our objective function phi by adding the quadratic term here, this one. So epsilon t is usually referred to as Tikhonov function. So this new function, phi epsilon, is a strongly convex function, right? Phi was a convex, phi epsilon by definition is strongly convex. The unique minimizer of a strongly convex function phi epsilon, x epsilon, is characterized by the first order optimality condition. Well, nothing special here. And now we link the gradient of the regularized function, which is basically here, to our second order in time differential equation. So instead of the gradient of the objective function, we have the gradient of the regularized function. And that's how we obtain this additional term, which is called, well, the Tikhonov term in the literature. And this additional term ensures the strong convergence of trajectories, not to any point, to a minimizer of from the set of all the minimizers of the projective function, but to the point of the minimum norm, to the minimum norm solution. And of course, this is the main role of having this term in our equation, but secondly, which is arguably even more important, we want to preserve the fast convergence of the function values to its minimum, because our initial goal was to minimize the function, the objective function. Yes. So this object x epsilon, which is the minimizer of the strongly convex function here, has some very nice properties. First of all, its norm is upper bounded by the norm of the minimum norm solution for all t greater or equal than t0. Secondly, which is more importantly, we have the following, that the limit of this norm when t goes to positive infinity is actually 0. So as I said, we want to prove the strong convergence of a trajectory to the minimum norm solution x star. How do we do this? First, we use the Lyapunov analysis to prove this fact, that the trajectory converges strongly to x epsilon, to this minimizer of our function, of our regularized function. And then combined with this fact together, after some manipulations, they give the actual strong convergence of the trajectories xt to x star, which is basically what we need. So this is just a brief idea, the sketch of the proof. Of course, much work has to be done. This is not trivial at all, proving this fact. But yeah, with the means of Lyapunov analysis, constructing Lyapunov function, proving its dissipativity, and so on, we are able to prove result of such a form. I specifically started with the continuous time methods because there it's very easy to see where does this Tikhanov term come from. But it could also be applied to the discrete time optimization, namely to the algorithms. And when we entered this topic, okay, so our initial goal was to construct an explicit algorithm. So without a proximal operator in its formulation, this one is implicit, it's a proximal point algorithm. But we wanted to get rid of this proximal operator here to apply Tikhanov regularization technique and to obtain the strong convergence of the iterates, which are the sequences generated by this algorithm, to a minimal norm solution. Now, the motivation is as follows. For the famous Nesterov algorithm, which enjoys the quadratic rate of convergence for the function values, still the convergence of its iterates is not known. So the question is still open whether the iterates generated by the classical Nesterov algorithm converge or not. Even weak convergence is not proved. Of course, we can modify it a bit, the so-called Nesterov type algorithms, and for them the weak convergence is very well known under some assumptions and under careful choices of following parameters. So we thought, okay, maybe we take Nesterov algorithm, we modify it by adding the Tikhanov regularization term, and maybe there will be hope to show strong convergence of the iterates and preserve the quadratic rate of convergence of the original Nesterov algorithm. So that's where we entered the topic. That was our main motivation. But first, a bit of history. So what was done before? As I said, there were plenty of proximal point algorithms in such a form, for instance, this one. For this, we know that sorry. Yes. Okay. First of all, as I said, this is a proximal point algorithm. So the next step is updated using the proximal point operator. Secondly, there is a Tikhanov regularization term here, a Tikhanov term here, this one. The fast convergence of the function values have been proved for this type of algorithms, and separately, the strong convergence of the iterates were proved. The strong convergence of the minimal norm solution of the iterates were also showed, but under different choices of parameters. So as we can see on this slide here, so this slide perfectly illustrates one of the problems with proximal point algorithms. We have two different settings. So under this choice of parameters, we have fast convergence of the function values and only weak convergence of the generated sequences. Under this choice of parameters, which obviously they don't intersect, we have a slightly worse convergence of the function values, and we have strong convergence of the iterates. So the problem is that we cannot have fast convergence of the function values and strong convergence of the iterates at the same time, because these settings don't intersect. different choices of parameters are required in order to obtain these two major results. This is one problem. The second problem is that in the most general case, we can obtain the following result, that the lim inf of this norm is 0, which basically means that there exists a subsequence, xkn, let's say, which converges strongly to the minimal norm solution. So not the whole sequence of generated iterates converges to the minimal norm solution, but a subsequence of it. And if we want to obtain the full strong convergence of the generated iterates to the minimal norm solution, then we have to impose additional very technical and pretty much unverifiable assumption that if the sequence lies either inside or outside this ball, then we have a full strong convergence. So these are two major problems: the separation of the results and this technical condition for the full strong convergence of our iterate. With that in mind, also keeping in mind what I said before, that we want to get rid of the proximal operator, which could be quite costly in terms of computations when we want to speak about applications. After many unsuccessful attempts, we were able to construct the following algorithm. This is a Nesterov type algorithm. It's an explicit one. The iterates are updated directly with the gradient of the objective function. And it features double Tikhonov regularization here, as we can see. And for this algorithm, we were able to show all the major results which were requested at the beginning. So the convergence of the function values to its minimum, and the strong convergence of the generated iterates to a minimal norm solution. And now, most importantly, now we don't have the separation of the results. This is just one big setting where we can prove everything which we need. Secondly, we have an unconditional strong convergence of the iterates. And thirdly, yes, this is an explicit algorithm without any proximal operator, without any proximal update. So let's consider some numerics. One may ask, what is the difference between weak and strong convergence in finite dimensional spaces where all the applications lie? Okay, there is no difference, obviously. But still, there is an influence of the Tikhonov term on the behavior of the iterates. And the influence is as follows. So let us consider a very simple objective function like this. Obviously, 0, 0 is the element of the minimal norm from all of its minimizers. Okay, first of all, the numerics show that the speed of convergence for the function values to its minimum is of the Nesterov type. So I'm not sure if you can see here, but okay, purple is the Nesterov choice of parameters, this one, and okay, the other lines are our algorithm with different choices of Tikhonov regularization. And you can see that they behave more or less, well, pretty similar, right? But this is not the most important thing. The most important thing is the what happened? Okay. The most important thing is the following. This really highlights the influence of the Tikhonov term even in finite dimensional spaces. What is plotted here? Here the trajectory is plotted. It is two-dimensional, and in red one component is plotted, in blue the other one. And we can see, so if at least one of the regularizations is absent, so either both are absent, both are 0, or at least one of it, we see the convergence of the iterates a minimizer from the set of all minimizers of the objective function. So on practice, let's consider a very simple one-dimensional case. Suppose that this is the set of the minimizers of our objective function phi. If we initialize here, then we'll converge to this point and then basically stop. If we initialize here, we converge here and again basically stop. And that's what we see on the second picture. We converge to a point from this set and then kind of stay there. But what Tikhonov regularization does, it ensures the convergence to the minimal norm solution, to the element of the minimal norm, which is in our case 0, 0. So no matter where we start, we will converge to the minimal norm. And the first picture illustrates this perfectly. You can see that both components of the generated trajectory converge to 0. One thing to mention here. For the polynomial choice of Tikhonov function, we can see that the rate of convergence of the function's values is 1 over k to the power of p, where p is between 0 and 2. Now the state-of-the-art rate convergence of convergence is 1 over k squared. As you can see here, we cannot really obtain the state-of-the-art rate of convergence for the function's values. P can be as close to 2 as we wish, but not exactly 2. And this is the price which we're willing to pay to guarantee the strong convergence of the controlled strong convergence of the iterates to the minimal norm solution. We lose something in the rates, but we get a huge improvement in the convergence of the iterates. So when I say controlled strong convergence, I mean the following. So what is written there? Basically, it is epsilon t, right, times xt minus 0. That's what is written there. If we replace 0 with, say, x0, an element from the Hilbert space, then we'll converge to the projection of x0 onto the set of the minimizers of the objective function. And that's what I mean by controlled strong convergence. We can actually, well, in a way, control to which element we converge by changing our initial equation, by adding some additional constants here. Thank you very much for your attention.
Thank you.